Today we want to talk about rate of change, or I should say we want to continue talking about rate of change. We want to make a few distinctions. These are also distinctions that we have already made. We want to talk about average rate of change versus instantaneous rate of change. The mathematical thing where we describe rate of change is slope. And we now have, since this is calculus class, two kinds of slope. We have a slope of a secant line, and we have a slope of a tangent line. And these represent two kinds of rates of change. Our average rate of change, how things are changing between two distinct points, and our instantaneous rate of change, what is happening at this moment. Your average rate of change would be something like you drive 400 miles in 5 hours. Your average rate of change was 80 miles per hour. On that trip, you were probably not driving a constant 80 miles per hour for the entire 5 hours. You probably started off at 0 miles per hour at the beginning of your trip, and you did not instantly accelerate to 80 miles per hour. So if your average was 80 miles per hour, your speedometer reading, your instantaneous rate of change, would have been a lot of different values. So your average rate of change is the slope of a secant line connecting 2 points. Started off at 0 miles, ended up at 400 miles in a time of 5 hours. Slope 80 miles per hour. But along that way, the tangent was different. Sometimes the tangent, if your average was 80 miles per hour, there were plenty of times where your speedometer reading was going to be probably well over 100. And there were a lot of times where you're at a stoplight and your tangent was going to be 0. So we talked about the slope of the secant line, the slope of the tangent line. This is the difference between average rate of change and instantaneous rate of change. I want to talk about today some common, easily identified rates of change. There are some functions that are defined by their rates of change. We like to classify functions in a lot of different ways. One of the ways that we classify functions is by their rates of change, not just what they look like, but how they are changing. So this is another way to classify functions. We're going to be classifying functions by their rates of change. And we're going to start with, of course, our favorites. Linear functions have a constant rate of change. This is the defining characteristic of a linear function. This is what makes them linear. Linear functions have a constant rate of change. We need to think about this in terms of the functions themselves. So let's write down a generic linear function. There's a linear function. The derivative of the function will be the rate of change. So derivative, rate of change, slope. These are things that we all want to mash together in our minds. So if we want to talk about the rate of change of this function, we need to look at the derivative of the function. So the derivative of this function the derivative of b bx to the 0 is 0b to the x, 0bx to the negative 1, so just 0. So the derivative is just the slope. M is the slope. The derivative of a linear function will just be the slope. There's the constant rate of change. Derivative is rate of change, derivative is constant. In terms of tangent lines, the tangent line to a linear function will just be the function itself. The linear function is its own tangent line because it is a line. We also want to recognize in the numbers how this constant rate of change expresses itself. So if I have a table of values for this function, when x is 0, f of x is equal to b. And every time x increases by 1, the function increases by m. That's how slope works. That's how linear functions work. We have this constant rate of change, a pattern of addition. So we add b one time when x is 1. When x is 2, we add m twice. When x is 3, we have added m 3 times, and so on. So what's happening is that the amount that we add is always the same. This is what linear functions do. This is why we like linear functions. We add m a bunch of times. There's our constant rate of change. Linear functions have a constant rate of change. Any questions? We all know linear functions well. Linear functions is our default mode of thinking as humans, so we like linear functions. Oh, whoops, I forgot. Spoiler alert, quadratic functions are going to be after this next example. So this also works for constant functions. Constant functions are linear functions. Constant functions are linear functions. Constant functions are also linear functions. The graph of a constant function is a horizontal line, and the slope is 0. So if I write down a constant function, I'll use k, the mortal constant. Then the derivative is 0. This tracks because a constant function, the graph of a constant function is a horizontal line. The slope of a horizontal line is 0. So this fits with all the stuff that we already know. There's our slope of 0. If we see this in the numbers, instead of writing plus m all the time, since the number ain't changing, we're just going to write plus 0. So we still have a constant rate of change. We're adding 0 when x increases by 1. Linear functions have a constant rate of change. This includes constant functions because constant functions are also linear functions. Now let's look at quadratic functions. It's going to go up 1 degree. Quadratic functions will have a linear rate of change. Quadratic function will have a linear rate of change. I need a more stable table because I keep Blair Witching this whole thing. I tried watching the Blair Witch Project when it first came out. Not in a theater. We had a bootleg copy somehow. I don't know. I have a friend that steals stuff. And I couldn't watch it. Not because it was frightening, but because the camera kept moving around and I am susceptible to motion sickness. So I'm like, oh man, I cannot watch this. I'm like, well, it's not that scary, Leech. What's wrong with you? It's like, well, no, I'm getting sick. I needed to take Dramamine for this. It was a long time ago. I was in college. We were drinking. I was taking the opposite of Dramamine. Anyway, try to be softer around the table. Quadratic functions have a linear rate of change. Of course, this makes sense because we do nx to the n minus 1. That n minus 1 is going to take our quadratic exponent of 2 and drop it down to a linear exponent 1. So if I write down a quadratic function, q of x equals ax squared plus bx plus c, then q prime will be 2ax plus b. It was at this point that we realized writing y equals mx plus b using b for the y-intercept. I guess it worked out in this case. It doesn't work out when we switch to exponential functions. I usually do exponential functions second. We'll see the problem then. But here is a linear rate of change. There is a linear rate of change. There is a linear rate of change. Because if I take another derivative, the derivative of this derivative, we get a constant. So we have a constant rate of change of the rate of change. Double rate of change. Second derivative. We can see this show up in a table of values when we see a linear rate of change. I'm going to pick the easiest quadratic function. I'm just going to use q of x equals x squared. We know that a quadratic function, just q of x equals x squared, will have a vertex at 0, 0. And then we can use the symmetry. If x is 1, g of x is 1. G of negative 1 is also 1. G of 2 is 4. G of negative 2 also 4. G of 3 is 9. G of negative 3 is 9. Now, if we look at the rate of change and we see how this function is changing, from 9 to 4, we subtract 5. Then we subtract 3, then we subtract 1, then we add 1, and then we add 3, and then we add 5. That is a linear function. That rate of change is a linear function. There's the linear rate of change in the numbers. 5, negative 3, negative 1, 1, 3, 5. The rate of change of that rate of change is constant. We start with a quadratic. The first derivative is linear. The second derivative will be constant. So the rate of change of the rate of change is positive 2. From negative 5 to negative 3, that's an increase of 2. Then another increase of 2. Then an increase of 2. Then an increase of 2. Then an increase of 2. A linear function has a constant rate of change. A quadratic function has a linear rate of change. This is for the function q of x equals 1x squared. And that second derivative was, as predicted, 2 times 1. So everything seems to fit so far. We want to be able to look at numbers and identify our linear functions. We do that by looking at how they're changing. If those functions have a constant rate of change, then those functions are linear. Any questions? How's everybody okay? This establishes a pattern. If I have a cubic function, that'll have a quadratic rate of change. This goes back to our shortcut, nx to the n minus 1. If I start with an x cubed, my first derivative will be an x squared. My second derivative will be an x to the first. My third derivative will be constant. My fourth derivative will be 0. So that we're gonna stop keeping moving forward on that, and we're gonna look at another kind of rate of change. I usually phrase the rate of change of an exponential function as being proportional. This is a very lazy way of saying this, but it's compact, so I like it. The big difference in an exponential function is we're changing not by addition, the change is tracked with multiplication. Exponential functions represent patterns of repeated multiplication. Exponential functions are repeated multiplication. That's why they're exponential functions, because exponents are repeated multiplication. Linear functions are repeated addition. That's why we mark the change with multiplication, because multiplication is repeated addition. So a linear function says b plus m times x. That's add m a bunch of times. Exponential functions, the variable shows up as the exponent because we're doing repeated multiplication. So here's an exponential function, 5 times 2 to the x. This function says start off at 5 and multiply by 2 a bunch of times. P of 0 is 5, and P is multiplied by 2 every unit. So how things are changing is with multiplication rather than addition. That's our sentence describing what's going on in this exponential function. Our description is very similar to that of a linear function, where y is b when x is 0, and y increases by m. We add m every unit. We've traded adding m every unit for multiplying by b every unit, or in this case, multiplying by 2. So the pattern that we're looking at here, when x is 0, p of 0 is 5. So p of 0 is 5, and our pattern is going to be to multiply by 2 every unit. So that means going backwards, we're going to be dividing by 2. So at -1, we'll have 2.5. When we identify the pattern of this exponential function, we identify multiplication. That's what makes it the exponential function. So we're repeatedly multiplying by 2. Start off at 5 and multiply by 2 a bunch of times. What I mean when I say the rate of change is proportional, that means if I have twice as much value in the function, my rate of change is going to be twice as much. When the function doubles, the rate of change doubles. So here we are with the multiplication. There's a pattern of repeated multiplication. That's the pattern of repeated multiplication. That's what we know about exponential functions. What we want to recognize is what's happening to the rate of change. What's happening to how much we're adding? What's happening to the slope as we go through this? What might the derivative be of this kind of function? So From 2.5 to 5, that's an increase of 2.5. From 5 to 10 is an increase of 10. Oh, sorry, 5. From 10 to 20 is an increase of 10. From 20 to 40 is an increase of 20. From 40 to 80 is an increase of 40. So what we're seeing is that the rate of change is also an exponential function. What we notice is that the rate of change is also an exponential function. One of our favorite things to model with exponential functions is population. And the idea here is that if the population is twice as big, it will be growing twice as fast. This course slows down eventually. Eventually it gets crowded. And at least in the case of humans, we start murdering each other. In the case of bacteria on a petri dish, we start running out of whatever jello they put on the petri dish to make bacteria grow. I didn't do biology. One of my favorite classes when I was an undergrad was chemistry. And then second favorite was physics. And then kind of like my third favorite was biology. And I realized why. Chemistry was the easiest one to reverse engineer. And then and once I started reverse engineering my labs, I go, oh, you want less than 5% error? How about 4.87? Would that be cool? All right, then I can work with that. And then I realized, like, well, maybe I shouldn't be like a chemist, and I should just be like a mathematician, since I'm just like cheating. This is like 40 years ago, so I mean, 30, it was a long time ago. Physics was only second place because there's just no way I could not make physics work. I remember I was doing physics 2, and we had these experimental capacitors, and we were supposed to be transferring charge around, and it never worked because the air conditioning was on. And so it's like, oh, this is not going to work. And they're like, oh, just keep trying. I'm like, oh yeah, I'll keep trying. What's supposed to happen? Yeah, okay, we can make that happen. My lab partner's like, oh, are you sure you're not just a mathematician? I'm like, oh, I got to be a physicist in here. So what we want to notice is that the rate of change is also an exponential function. This pattern that's the same pattern of repeated multiplication. And that's an important thing to notice. It's that same pattern of repeated multiplication. One of the things that we want to notice is that I'm taking rate of change and slope and derivative, and I'm kind of throwing all those things together, because in our minds, we want to throw all those things together. We want to make distinctions between like average rate of change and instantaneous rate of change. That's the one that's the derivative. And we're looking at some average rates of change over a delta x of 1, but we still want to make those connections. I want rate of change to be slope to be derivative. I want all those things connected in your mind. The reason is eventually we're going to find all these derivatives. We're going to learn some arcane rules for finding derivatives, and it'll be super fun. And eventually someone will be like, oh, dude, why are we finding all these derivatives? What are the applications of derivatives? And we can always easily back out to say applications of derivatives are applications of slope. Anytime we are looking for a rate of change, we're looking for a slope. That's a derivative question. The same thing is going to happen when we get to integration, which is even going to be more arcane and weird and therefore fun. And we're going to think, what are the applications of integration? And we can just back up one step, generalize, and say, applications of integration are just applications of multiplication, because integration is just fancy multiplication. Derivatives are just finding slopes. So anywhere we care about the slope, anywhere we care about how one variable is changing with respect to the other variable, that's an application of derivative. In this case, we get an interesting thing because we described an exponential function as a proportional rate of change. So what we're saying is that p prime of x is just some constant times p of x. This is saying that the rate of change of an exponential function is proportional to the function. That's what this equation is saying. We're saying the rate of change I wrote the derivative of this exponential function. The rate of change, that's another word for derivative. The rate of change of this exponential function is proportional to the function. The rate of change of an exponential function is proportional to the exponential function. That's what this differential equation is saying. That means that if p of x is twice as big, then your rate of change will be twice as big. Double the population will grow twice as fast. These would be three functions that I would want us to recognize based on their rates of change, so that when we're looking at data, we can see if this is going to be a fit. I also algebraically like these two linear functions and exponential functions to be put together, because linear functions are a pattern of repeated multiplication. Linear functions use multiplication to represent a pattern of repeated addition, m times x. Exponential functions use exponents to represent a pattern of repeated multiplication, 2 to the x. Multiply by 2 a bunch of times. Any questions? Comments? Slide remark? We also care about exponential functions because when things increase by a percent or decrease by a percent, we are making an exponential function, using an exponential function as a model. So when we say something like multiplied by 2, that's the same thing as saying increase by 100%. So multiply by 2 is equivalent to increase by 100%. When we see things increasing by percentages, we are seeing things increase exponentially. An increase or decrease by a percentage means we're experiencing exponential growth and decay. I like to make this distinction because a lot of times we want to try to sound fancy by saying something, when something is growing fast, saying something is growing exponentially. Because we sound fancy if we say, wow, this is growing exponentially. We sound fancy. But if we're saying that, we're saying something very specific. There's some kind of percentage. So as soon as someone says, well, it's growing exponentially, I'm like, oh, what percent is it growing by? And then they have to be like, oh, no, I just mean it's growing fast. And just fucking say fast, man. Do you know what I mean? Don't be trying to sound fancy. Heard a newscaster talk about someone's athletic performance growing logarithmically because they wanted to sound fancy. It's like, oh, that's kind of sick. It's like, oh, that's kind of like implies like, oh, they're peaking soon. It's kind of their increase is slowing the fuck down. So, don't try to sound fancy. You know what I mean? Just say fast if you're not sure. It's, wow, it's growing fast. The audience that works on, it doesn't matter anyway. You know what I mean? It's like, oh, they said exponentially. That sounds fancy. They must be smart. If that's going to work, those people aren't worth impressing. I mean, you know what I mean? It's a lot of times you'll hear me say things in class and you think, man, Leach must be a pain in the ass to have a conversation with. And I just want to assure you that that's kind of 100% true. If you start throwing math terms around, I try to stop. I don't want to be that guy, but I'm like, oh, it's like literally my job, and it's hard to turn off. You know what I mean? It's especially annoying when you have gaming friends. I play tabletop role-playing games, and I have one friend that's always like introducing new systems. It's like, I like this because it's more of a feel thing and less of a mathematical analysis thing. I'm like, oh, and like I had in my hand like a folder with like a detailed mathematical analysis. I'm like, oh yeah, no, I see what you mean. And I go, Leach, did you do a mathematical analysis of success rates? No, I don't know what you're talking about. It's not like I even care about optimized characters. I just want to know. You know what I mean? It's like, oh, that will get you a boost die. I want to know how much that changes. You know what I mean? So an increase or a decrease by a percent will represent exponential growth and decay. So if we see something that says increase by 15%, we can translate that to multiply by 1.15. The 1 represents the 100% that you get to keep. That's 100%. If it's increasing by 0%, we will multiply by 1. Adding 0 is no change. Multiplying by 1 is no change. So if we increase by 15%, then we'll multiply by 1.15. 1 for the 100% that we get to keep, 0.15 for the 15% extra. If it was decrease by 15%, Then we'll multiply by 0.85. We take the 100% that we start with and we would subtract 15%. Calculators used to have a percent button, so you would put like 1999 plus 9%, and it would just multiply by 1.09. Because rather than teach people multiply by 1.09, we put a whole ass extra button on the calculator to do that for you. You know what I mean? And now we don't even know what percent means anymore. I mean, we think we do, but we use our intuition on it and makes it kind of shitty. It's like I'll have like a class with like 12 people and they go, what percent passed? And I go, motherfucker, there were 12 people in the room. Percent would be a dumb way to do it because there were 12. Percent means per 100. You know what I mean? And it doesn't even hold up because like a class of 12 is going to be so different than a class of 100. So you can't take what you did with 12 students and think, well, if you had 100 students, look how much. No, that's just not how it works. You know what I mean? So yeah, I still do it for points. Contradictions, I guess. All right, those are three kinds of functions you want to identify by their rate of change, aka slope, aka derivative. Remember, derivative is the big thing. Rate of change is the way we're going to think about it. That's going to do it for today. I will see you all on the morrow. Everybody have a good day, and thanks for playing.